Here's a way to compute the cross product you might not have seen before. Let's say you have two vectors you want to take the cross product of that we'll call A and B, and we'll call their x, y, and z entries ax, ay, az, and bx, by, bz respectively. What we're going to do is that we're going to make a matrix out of this first vector here. Let's call it capital A, I know, really creative. And here's how you're going to make this new matrix. In the diagonals, you're just going to put zeros. 0, 0, and 0. And then you're going to fill out the rest of the entries like this, okay? So, look at our third entry, AZ, you're going to put its negative right here. Negative AZ. Then you'll take the second entry, AY, leave it the same way. And then you'll put the opposite sign of this first term here, negative AX. That's how you fill out the upper triangle part. And in the lower triangle, you're just going to do the exact opposite of that. The mirror image, really, when you're reflecting across this triangle. So if you have negative AZ over here, reflecting that over, you'll have positive AZ over here, negative AY down here, and then positive AX right here. Once we have this matrix, what you're going to do is that you're going to take this matrix and multiply it by that second vector that you had. And it turns out that the matrix that pops out of this operation is always going to be the cross product of those two vectors. Let's go ahead and try out this matrix formula and see how it works. So I want to take the cross product of the vector 1, 2, 3 with the vector 4, 5, 6. So setting up our matrix, it's going to look like 0, minus 3, 2, 3, 0, minus 1, and negative 2, 1, 0. And then we go ahead and leave the second vector as is, and let's multiply through. So 0 times 4 is 0, negative 3 times 5 is negative 15, 2 times 6 is 12, and then 3 times 4 is 12, 0 times 5 is 0, minus 1 times 6 is minus 6, and then negative 2 times 4 is negative 8, 1 times 5 is positive 5, 0 times 6 is 0, and so we go ahead and simplify from here. So negative 15 plus 12 is negative 3, 12 minus 6 is 6, and negative 8 plus 5 is negative 3. Let's see what happens when we take the cross product in the usual way now. So we start off by setting up our matrix, and then we take the determinant of it. So we have 2 times 6 is 12, minus 3 times 5 is 15, and that's going to be our I hat entry. Minus, we're going to have 1 times 6 is 6, minus 3 times 4 is 12. It's going to be our j hat entry, plus 1 times 5 is 5, minus 2 times 4 is 8 is going to be our k hat entry. And this will go ahead and simplify to negative 3 I hat plus 6 j hat minus 3 k hat. Or written in the usual vector notation, negative 3, 6, negative 3. Now maybe you're about to click away from this video because you like cute little computation tricks like this. This is all you need. And that's fine, more power to you. But some of you are a little suspicious. Why should this work? And how do you know I didn't just cherry pick an example where that would work? You want to understand why this works in general. Well, let's take a look at it. Let's get under the hood a bit. The proof is remarkably simple. All you have to do is write out the formulas. So if I have two arbitrary vectors, A, B, C, and I cross it with D, E, F, well, when I set up my matrix in this way, and then multiply it by B, E, F, this is what I get. B, F minus C, E, C, D minus A, F, and A, F minus B, D. But if I take it using the determinant approach, well, then what do I get? Well, for the I hat entry, that's B, F minus C, E. For the J hat entry, C, D minus A, F. And the K hat entry, A, F minus B, D. Notice that I swapped these around because when you take the negative of a negative, you get a positive. So, something to watch out there for. This still leaves one question unanswered though. Why would you expect this to work in the first place? After all, someone had to have discovered this fact, and why would you just think that you can multiply a matrix and get the same effect as if you'd just taken the cross product? Now, why would you expect to even be able to write the cross product as a matrix product in the first place? Well, here's one way you can think about it. Let's say we pick any vector we want. We're just going to call it A for now, and then we can imagine that we cross this with just some blank. We've created sort of a function here, right? Where the operation is you input some vector, and the output is whatever the cross product is whenever you get A across this new vector. So here's our input, and it outputs whatever this cross product is. Now you notice this is a function that takes in vectors and spits out another vector. And if you know your cross product properties, you know that A cross some scalar is going to be some scalar times the output. And we also know that this thing distributes over addition as well. Meaning that not only does it take in vectors and spits out vectors, it does so in a linear way. This is a linear map. And as you know, linear maps can be represented by matrices. If you're familiar with your properties of the cross product, you know that if you take A cross B and then just switch the order to B cross A, that should give you the negative of this, right? And this is important because we can actually learn more about this matrix thing that we expect here. Watch this. We can have the blank be the first vector, and this will give us a new matrix function, right? This time, the first blank is the input. And this will give us the negative whatever the other function is. Now, before we can see why that switching the order fact is important, we need to remind ourselves of how multiplying a matrix by a vector works real quick. So, if you have some matrix times a vector, you get some vector out of it, right? Some vertical vector here. But when you switch the order and do the vector times the matrix, then you need to turn this vertical vector into a horizontal one, because the number of columns has to equal the number of rows in order for the dimensions to line up. And also the output is going to give us another horizontal vector. So we know that our matrix times some vector b is going to give us a new vector c. So if we switch the order then we know that b, we got to turn it sideways, so we'll take its transpose and multiply it by a, and that's going to give us negative c, but again it's sideways, so we got to take the transpose again. Notice that we can take the transpose of both sides again to make it match the original, right? So transpose of this, so we get a transpose b is equal to negative c. So in order for these two expressions to line up, what we have to conclude is that the matrix A is equal to the negative of its transpose. A matrix with the property that when you flip it along its diagonal, you get the negative of the original matrix is called a skew-symmetric matrix. Often written down in this equation right here, A equals negative A transpose. So if we have L over here, you have negative L over here, M over here, negative M over here, and so on. Notice, by the way, that the diagonal of this matrix must be 0, right? Because the diagonal stays fixed, and the only way the positive version number can equal its negative version is if the number is 0. Notice, this is exactly like the matrix I was showing you at the beginning of this video. And it's not too hard to see that if you want to make this equal the cross product you're used to, you just got to pick entries for L, M, and N that make it work the way you need it to. You just force it to match the cross product formula. It gets even better than that, because we have the following theorem that shows how this is related to the usual geometric interpretation of the cross product. So a matrix is skew-symmetric if and only if you take it and multiply it by some vector, that output, and you dot it with the original vector, it equals 0. Feel free to try to prove this for yourself. But remember that the dot product of two vectors is 0 when they're perpendicular, or if one of them is 0. But that means that this interpretation tells us that this must spit out a vector that's perpendicular to the original. It is the cross product. Well, that's all for today. Don't forget to let me know if you have any comments, questions, or suggestions in the comments down below. And feel free to like, share, subscribe, and send this to a friend who you think might find this interesting or helpful. And don't forget, when life gives you lemmas, make lemonade.